Welcome back to our discussion on states of matter. It's our sixth round of classes or discussions on states of matter. We rounded up yesterday's discussion by looking at kinetic theory of gases. So, a quick recap of what we discussed. We said there are three primary parts to this. One deals with molecules, that the molecules of a gas have all the mass and occupy zero volume. Of course, there is also the Dalton postulate, which says that all molecules in the gas will have identical masses, which I have not added here. The second big thing is about motion of molecules in gases. We said that it takes straight line paths, moves in straight lines until it undergoes a collision either with the walls of the container or with another molecule. We also have that the rate or the velocity, rate and direction of motion is random. That the kinetic energy is proportional to temperature, and parts of that also says that the average kinetic energy of all molecules is same for all molecules. And there is conservation of energy and momentum during a collision. And then the third part of it deals with Avogadros postulate or hypothesis, whatever you want to call it, which says that equal volumes of all gases at same temperature and pressure contain the same number of molecules, which is used in this kinetic theory of gases. So, we also discussed about how this pressure comes about, although we did not do the derivation, that the pressure arises as a result of collision. Collision with the walls of the container. Okay. And that because it is dependent on the velocity and the kinetic energy is then proportional to the temperature, we can then show that pressure is a function of the temperature. Okay, let us move on. What we said is that we would now like to try and derive the ideal gas, not derive, at least talk about the ideal gas equation. So, if you look at Boyle's law says that V is proportional to 1 over P at constant T and for fixed mass. So, we rewrite this a little bit and we say that PV, the product of P and V, is a constant. Let me call this constant K. Now, for a fixed mass. So, because the temperature is constant, we now write that K can be written as K small k times T, where we say that because this is true because the temperature is constant. So, I say that PV equals kT. This is the deduction from Boyle's law. Now, at constant volume or at constant pressure, first we say that V is equal to kT over P, and because temperature is constant, pressure is a constant. No, for the same mass of gas, K is a constant, pressure is a constant. So, what this tells you is that V is proportional to T, which is exactly Gay-Lussac's law. So, from Boyle's law, that PV equals kT, or for a fixed mass of gas, we are able to get back Gay-Lussac's or Charles' law. Similarly, starting with the same thing, at fixed volume, we say P is equal to K over V times T, and since both of these are a constant, we are saying that P is proportional to T, which is in some sense another form of the Gay-Lussac law. Although we did not discuss it, Gay-Lussac did it for volume proportional to temperature. This is a result that follows from Gay-Lussac's law. So, what we get is that PV is equal to kT satisfies the properties of gases that we discussed, and this PV is equal to kT, although we did not go through the complete discussion. This arises as a result of the assumptions this is a result of the assumptions that we have that are in the kinetic theory of gases, the kinetic theory of gases. So, what are we saying? We had some assumptions which we call the kinetic model or the kinetic theory of gases, the kinetic molecular model of gases, and as a result of this kinetic molecular model of gases, we were able to draw conclusions which seems to go in accordance with the properties of gases, right. And the result of all this is telling you that the product PV for gases that satisfy the kinetic molecular model is proportional to temperature. That is what this is telling you. So, we have constructed a model, and the model has the assumptions which are part of the kinetic theory of gases, which we have just discussed, and a result of this model is that we are saying that the product PV is proportional to the temperature. It might be at this point a good idea to look at what it means a little bit. P has the units of force over the area, and the volume is nothing but area times a length. So, the left hand side has units of energy. So, PV has units of energy. So, if you were to express the volume in liters, which used to be the norm a few years ago, a few tens of years ago, then and the pressure in atmospheres, the PV product will work out to be liter atmospheres, and we are saying that this product is the same as corresponds to the unit of energy, which in SI units would be joules. So, this product of K times T has to have units of energy, okay, which is one of the reasons why we said that the kinetic energy, you can say, is related to the temperature through this constant. Okay. So, that allows you this deduction between kinetic energy and the temperature. Okay. So, now any gas which satisfies this relation PV equals kT is called an ideal gas. So, if a gas satisfies this relation PV equals kT, it is called an ideal gas. And you can derive this in any way you wish. You can say that V is proportional to 1 over P, V is proportional to T, and V is proportional to N, and you will get this relationship for the ideal gas. But for the moment, let us not worry about that derivation. Let us see if it is indeed really true by looking at some experimental values. So, we take a sample of helium and we take as much mass of helium such that at 0 degrees Celsius, which is 273.15 Kelvin. So, we take as much mass of helium such that at 0 degrees Celsius it occupies 1 liter at 1 atmosphere pressure. So, let us take this sample and then vary the temperature and look at the PV product. So, if what we are saying is right, what we are saying is, though, if you have temperature and you look at the PV product, I am writing the temperature in degrees Celsius, which means that if you want to convert it to Kelvin, you will have to add 273.15 to it, and these are expressed in units of liter atmospheres. So, we started off by saying at 0 degrees, we have this product is 1.00. At 50 degrees, this happens to be 1.183, and at 100 degrees Celsius, this product is 1.3659. And you could go down at minus 50 degrees, it is 0.8171. At minus 100 degrees, it is 0.6341, and the list goes on. Already you start to see a trend. As the temperature goes down, this PV product goes down. And if you wish to convert this into Kelvin, you say T in Kelvin is this column, whatever you have, plus 273.15. So, that will be, in this particular case, 373.15, and so you can do this for the others. So, if I now plotted, what we are saying is, one of the deductions of the kinetic molecular model is that if I plotted PV product as a function of the temperature, and here I am doing again degrees Celsius, if I plotted this, I have some range, mark off this at 100 degrees. So, this is at 100 degrees Celsius and this is at 0 degrees Celsius. This is 1 for the sample that we looked at, and this happens to be 1.366 or so. So, if you are paying careful attention, these numbers that we have got are exactly the same thing that Gay-Lussac found. So, it looks very similar to the table that Gay-Lussac had of V being proportional to the temperature. And if you extrapolated this, this point where it cuts the x-axis is again minus 273.15 degrees Celsius. So, rather than derive the ideal gas equation, which is there and which you probably can do very straightforwardly, what we have now shown is that experimentally we find that this PV product actually does look like a straight line. So, we are saying that this is equal to this, and this slope, just mind you that when you are doing this, do it in Kelvin. if you do this, you will get this slope, which is the rise over the run. So, this is called the rise and this is called the run, which means that if you went this many degrees on the x axis, how much does the PV product increase? This rise over the run is the slope of this line. So, if you plotted this in Kelvin, so if I draw another scale here, if I draw another scale where temperature, so maybe I should call this rather than T, I will call this T prime for convenience. So, because this is in degrees Celsius and this is T, where T is equal to T prime plus 273.15 and this is expressed in Kelvin. So, what we are saying is at this point this corresponds to 0. So, if I plotted it on the Kelvin scale of temperature, this will pass through 0 because this has no intercept, and this slope would correspond to this rise. For every degree rise in temperature, how much is the slope of this line? So, higher this slope is, the more sloped this is. So, this is rise over run is equal to the slope. Just mind you that we are plotting it against the absolute temperature, not the Celsius, although it looks linear, but it cuts this axis at minus 273.15, but if you wanted to do it right, you have to do it on the absolute scale. Now, it is natural for us to look at it in Celsius, but when you are doing calculations, as I already remarked, you should do it, it is preferable to do it in absolute temperature. Okay. So, this is telling you, and this is the result of the model that we have, it tells you that the PV product is actually proportional to the temperature. So, the net result of all this is PV is proportional to T, and we are saying that if a gas satisfies this model, it is called an ideal gas. So, let us just try and look at this a little bit differently to get an idea of what is the value of K. So, again we will consider helium, and we know that the density, what we would like to do is to determine the volume of 1 mole of helium gas at 273 Kelvin, that is at 0 degrees Celsius and at 1 atmospheric pressure. That is what we would like to do. So, the volume occupied by 1 mole of helium at 0 Celsius, that is 273.15. Very often people drop the 15 and say 273 Kelvin and 1 atm pressure. And this has a particular name, because it is the volume occupied by 1 mole of this, this is called the molar volume. And how do we determine the molar volume? We determine the molar volume, we know that density is mass over volume, and we know that 1 mole, the molecular weight or the molecular mass of helium is is 4 point something grams per mole. So, from an idea of the density, we can compute the molar volume, and this molar volume happens to be, so for the density, if you looked up some data book, this would work out to be 4.003 grams over 0.1785 gram per liter, which works out to be 22.43 liters. You will notice that I am not using SI units, and there is a reason for this. This is because many of these numbers are familiar to people. So, it is good idea to do this in liters, but if you wish to convert it into SI units, you could do this straightforwardly. So, what we are saying is that the molar volume at 273 Kelvin and 1 atm pressure, which in the old days used to be called STP, but no longer used anymore. So, at STP, the old STP, the molar volume of helium is 22.43 liters, and if you have 1 mole, we have Avogadro number of molecules. That is the Avogadros hypothesis. So, Avogadro number of molecules. And by the Avogadros hypothesis, if we took other gases under identical conditions. So, if I took, what we are saying is, if we took equal volumes of all gases at the same temperature and pressure, would have the same number of molecules. So, if I take the same number of molecules, that is, if I took 1 mole of nitrogen or 1 mole of air or anything like that, the molar volume would in this model be the same quantity. We are just applying Avogadros hypothesis in reverse. So, we are saying that if I took 1 mole of the gas at any gas at 273 Kelvin and at subjected to 1 atmospheric pressure, the molar volume would be predicted to be 22.43 liters approximately. And it turns out that in reality most gases have a molar volume close to, but not equal to this. So, it seems like it is partly true. It is important that you remember this. Most gases, so what we do now, we are saying is that we have done this for helium. We have taken 1 mole of helium at 273 Kelvin, that is 0 Celsius, and 1 atm pressure, and we measure the volume, that is the molar volume of helium. Now, we are saying that if I took any other gas, that is 1 mole of nitrogen at 273 Kelvin and 1 atm pressure, according to Avogadros hypothesis, all gases should occupy 22.4 liters at 0 degrees Celsius and 1 atm pressure. Well, we can just take a look at the numbers if this happens to be true. Here is a molecule, here is helium. I am just writing the number of electrons in the molecule, 2 electrons in the molecule, and the molar volume in liters per mole, that is 22.415. If I looked at hydrogen, which also has 2 electrons, it is 22.428. If I look at ammonia, which has 10 electrons, 7 from the nitrogen, 3 from the hydrogens, 22.00077. CH4, which has 10 electrons too, has 22.36. Neon, 22.428, and the list goes on. So, we are saying that it is close to, but not identical, and this is something that we will come back to later. And this difference between what we expect from this and what we observe has something to do with the kind of behavior that happens if that gases show in reality. We will come back to that, but it is just important that you realize that this product is close to, but not identical to 22.4 liters. And what is this model that we have of a, so we have this molecular nature of the ideal gas. And what are the ingredients of this molecular model of an ideal gas? And all of it, when I write it down, you will notice comes directly from the kinetic theory of gases. So, this model, according to this, for the ideal gases, we know that the mass of gases is due to molecules. The volume of a gas is the space between molecules. Molecules are in motion at all temperatures, greater than 0 Kelvin and in straight lines. And they move at random, the molecules move at random. And the average kinetic energy is proportional to the absolute temperature, and when molecules collide, they conserve energy and momentum. And lastly, at any temperature, equal volumes of all gases contain equal number of molecules. Okay? So, these sort of ingredients of the molecular nature of the ideal gas, but we still have not figured out what the value of K is. So, let us try and go back and figure out what the value of K is in this expression for PV equals KT. How does one go about this? We know, so we take 1 mole of helium, and we know it occupies a volume equals 22.4 liters, and the pressure equals 1 atmosphere. So, then at 273 Kelvin. So, if you work this out, this PV product is 1 atm times 22.4 liters per mole, that is the molar volume. So, that is why I have per mole at 273 Kelvin. And the units, multiply the units out, this works out to be 0.082 liter atmosphere per Kelvin per mole. And this product we know is the energy. So, if you were to do it in SI units, this would work out to joule. This number would obviously be a little bit different. It will work out to be 8.314 joules per Kelvin per mole if you were to do it in SI units. Now, if you did the same thing for 2 moles, what do you find? If you did the same operation, so you do, so this K here is a function of pressure, volume and temperature, right. So, if I now did this for 2 moles, because this thing is per mole. So, if I did this for 2 moles, you will find, so for 2 moles you find that K works out to be 0.164 liter atmospheres per Kelvin, because this moles will go away with 2 times 2 moles. So, that works out to liter atmosphere per Kelvin. So, K, so if I were to do this 1 mole, so then I will get liter atmosphere Kelvin. This since I am doing it for 1 mole, this works out to be this. So, we can now say that K will be something n, where n is the number of moles of the gas times a constant which we call R, which will have units of liter atmosphere per Kelvin per mole. And this quantity here is called the universal gas constant. So, no matter which gas you take, this is independent of the gas that you have. So, now you could rewrite this as PV. So, rather than write it as KT, we will write it as nRT, where n has units of moles, this has units of liter atmosphere per Kelvin per mole, and this is in Kelvin. So, if I took this product, this will work out to be liter atmosphere per Kelvin, and this this will work out to be liter atmospheres, which is the product PV, and this has the same, this is, if you were to do it in joules, it will be joules, okay, because this has the units of energy. So, one of the things that arises from the kinetic theory of gases, and that is very important, with the validity of the kinetic theory of gases, from which we got the ideal gas equation, is critically dependent upon the conservation of energy. When molecules collide. So, imagine that I have a molecule A and I have a molecule B. Imagine that B is steady in something like this. You have a molecule A which comes and collides with B. What the conservation of energy is telling you is that if you call this VA and this as VB, and imagine this was initially 0, that is the initial velocity before collision, what we are saying is half m VA 0 square plus half m VB square 0 is equal to half m VA square T plus half m VB square T, where T is after the collision, and we are saying that this is equal, and physically you can understand what is happening. If this were not true, experimentally what would happen? Imagine that you had filled a bicycle tire or bicycle tube with gas, and what we are saying is when they collide, if this were not true, imagine that two molecules came, the two molecules in the air that is there inside your bicycle tube, they came in such that the total energy is something, and they collided, and we are saying let us imagine that when this happens the energy goes down, and if the energy goes down, let us imagine that it happens, then if that were the case, if this were not true, what would happen is with time the energy of the molecules will go down, because every time there is a collision the energy is going down. And if that goes down, then the volume will go down, because according to the kinetic model, motion is related to temperature, and without molecules or without the gas diffusing out of the tube, you are going to have that the volume will slowly decay and go down to 0. And we know experimentally that if you filled a tube in your cycle, if you filled air into it, it stays there. It does go, but that is for a different reason. There the number of, without, here what we are saying, without the molecules, number of molecules changing, we are saying that the energy will drop, and if the energy drops, since it is related to motion, the volume will go down to 0 and your tube will turn flat. But we know experimentally that does not happen with time. It does happen practically, but that is for a different reason, because the molecules or the tube is not completely diffusion free. So, molecules, so the gas actually escapes through the tube over time. So, n is changing here there. In this case, we are considering where the n does not change. So, without n changing, you cannot have this loose energy. So, this is critically dependent on this, that you have conservation of energy. Then you would ask the question that if I heated a gas which is in a container, how does the energy of the gas rise, as a result of which how does the kinetic energy of the molecule rise? Presumably it happens because a molecule in the gas phase comes and collides with the gas wall, and there again there is a conservation of energy and molecules. So, you can have transfer of energy. So, imagine I have 100 rupees, I go to a shopkeeper and buy something for 50 rupees, I have 50 rupees left and he has 50 rupees. The amount of money is conserved between the two of us, and I can redistribute it in any way I want. I can have 0 and he can have 100. The same way the molecules could redistribute the energy amongst themselves in any way. But if I came with some total amount of energy in the two molecules, it has got to be the same. If it did not happen, then the energy will go down and the volume will go to 0, which we know is experimentally not true. Now, what we are saying is, if I took the gas molecules in here and if I raise the temperature of the container, and once equilibrium is established, the gas will also attain the same temperature as the container. Now, if that happened, the only way that this could happen with the conservation of energy is that there is a transfer of energy from the wall to the gas, which means that the molecules that compose this container also have kinetic energy. That is a very, very important thing, right. What this means is that the solid also has kinetic energy, otherwise how will it transfer energy to the gas molecules, if this is true? If this is true, the only way that it could happen is that the walls of the container also are vibrating. Well, I am not, well, we know that it has to have energy other than translational motion, because I have a container here and the container is not moving, which means that it is energy of a different kind. But transfer of energy happens from the walls of the container to the gas, otherwise the temperature will not rise in this model. So, that automatically tells you that this kinetic model that we have used for the gases also applies to solids. It is also undergoing motion, except that it is rigid. So, the attractive forces that hold the solid molecules together are higher than what the kinetic energy can provide. So, it is undergoing motion, but of a different kind. So, you can extend this model to solids, and then you will say, and you know that the density is of the solid is much higher than that of a gas, which means so that the molecules are packed very tightly, but they are undergoing motion. and the same can be extended. So, if I raise the temperature, the solid will melt and I still have motion in the liquid. So, each molecule in a solid is surrounded by other molecules, and when it goes into a liquid, it still has to break free from this. So, this model can be extended to solid, and this is something that is critical for you to appreciate, that the gas molecules picks up energy. When I put this gas into a container, I keep it at some temperature, let us say 30 degrees, and I now take this thing and I raise it to 100 degrees. All that I have done is taken the container and put it on a Bunsen burner. So, which picks up heat? It is picked up first by the solid container, and the solid container molecules then transfer the energy in this model to the gas molecules, which then finally attains the temperature. So, this model can also be extended to the solid phase. Okay. So, but this is very critical thing about the kinetic theory. So, we have experimental evidence that this is true. So, if I take a bicycle tube, it does not deflate with time without gas molecules being lost, and if I raise the temperature of the container, there is transfer of energy from the solid to the gas. Okay. So, finally, if you go and looked at it, what do we have? This is the ideal gas equation of state, and for most things that you would be employing, all that you will need to do is to use this as a calculational tool, is to use the ideal gas equation of state, as it is called, as a calculational tool. Now, because molecules are not interacting in this model and that there is no attraction and they can move in straight lines, if I had a mixture of gases, as for example in the atmosphere, so I can just extend this. I say that P V is equal to N1 plus N2 plus N3 plus dot 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 R T, where I have a mixture of many gases. And this thing here is nothing but Dalton's law. So, if I rewrite this a little bit, you could say that P is equal to 1 over V N1 plus N2 plus N3 plus dot 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 R T, and each of these contributions. So, N1 R T over V plus N2 R T over V plus N3 R T over V, and so on, is the contribution from each one of the gases in the mixture. So, this is the contribution due to P1, this is the contribution to 2, and this is the contribution from 3, and so on, and this is the Dalton's law of partial pressures. So, the total pressure that we see in a mixture of gases will be the sum of the partial pressures. And you could rewrite this a little bit differently. Ni is equal to Xi over N, where this is the mole fraction. So, you could take N out common and then rewrite this a little bit, and so you can rewrite it in terms of the partial pressure. So, this is something that falls out of this. So, we looked at Dalton's law of partial pressures too. All right. So, let us now try and use this as a calculational device. Let us use the ideal gas law in the next few minutes. What we will do is to look at a few examples of being able to apply what you would be able to, you should be able to do is to use the ideal gas equation to apply it in some situations. Okay, something to start off with for people who are interested. So, these are some numerical examples. So, to start off with, let us address the people who are interested in football. By the laws of the game, a football, this is as per the FIFA rules, by the way. A football must be 68 centimeters to 70 centimeters in circumference and must be inflated to a pressure of 0.6 atm to 1.1 atm pressure. So, the question is, how many moles of air does a typical football contain? That is the question before us. So, we have a football, and this is what we say is the circumference that is accepted by FIFA, and it has to be inflated to this much pressure. So, imagine that you are playing the game at a place where the temperature is 27 degrees Celsius for convenience. So, although it is not given in this, let us imagine that it is anyway, there is a little bit of variability. So, let us imagine that it is 27 degrees Celsius. Okay? So, how would one go about it? So, let us just write out what we know. We could use this, right? PV equals nRT. And what we have to do is to compute this. So, to be determined. We know this pressure. It says 0.6 atmospheres to 1.1 atmospheres. Now, the question in your minds will probably be, what value should I use? Well, the easiest thing is to use the simplest calculational device, say it is 1 atmosphere. And I have chosen the temperature also appropriately. I have chosen it to be in 27 Celsius, so T is 27 degrees Celsius, which works out to be 300 Kelvin. So, this is 300 Kelvin. So, I have taken this, added 273, and you would have noticed I have dropped the 15, that is good enough, 0.15. So, I write it as 300 Kelvin just to get you a ballpark figure, and we need to know the volume. We say its circumference is between 68 centimeters and 70 centimeters. So, we say 2 pi r is equal to 70 centimeters for convenience, from which you can get the r of the football. And we get the volume, taking it to be a sphere. So, we have the pressure, we have the volume after doing this computation, we know the temperature, and you could use 0.082 liter atmospheres per Kelvin per mole. So, if you plug it all in, what are you going to get? Well, get it into the right units, make sure that the units are right, and in this particular case it would be right. So, we will say P is 1 atm, this is 4 by 3 pi r cube, and you will get this in centimeter cube. Is equal to n in moles into 0.082 liter atmosphere per Kelvin per mole into 300 Kelvin, and we know that 1000 cc's equals 1 liter. So, if you get this right, you will say 1 atmosphere times 4 by 3 pi r cube in centimeter cube, 1 liter over 1000 centimeter cube is equal to n in moles times 0.082 0.082 liter atmosphere per Kelvin per mole into 300 Kelvin, and you should get your units right. And that, whatever, you solve for this and you will get n in moles. So, that gives you a straightforward illustration of the number of moles. Well, fortunately, you do not have to worry about what the molecular weight in this particular case. All right. Here is another example. I am sure many of you have come across aerosol sprays, that is, things that are used. Well, one of the things that people use it for is deodorant sprays, right? It is called an aerosol spray. So, an aerosol spray can, with a volume of 350 milliliters, contains 3.2 grams of propane gas as propellant. So, whatever you have in that aerosol spray, if you want to get it out, you need to have a gas which will propel it out, and so that is what it is. So, this is the volume of the aerosol spray, and it contains 3.2 grams of propane gas, and we are asked what is the pressure in atmospheres of the gas in the can at 20 degrees Celsius. So, we know V is 350 milliliters. For convenience, we will write it in liters. So, when we are asked to compute the pressure, and the temperature is 293 Kelvin, which is 20 Celsius plus 273, right? That is what we have got. And do we know N? N is what? N is the number of moles of propane gas. Propane happens to be this 3H3CH2CH3. So, the molecular mass of propane. So, how do we get N, which is what we need? N is mass divided by molar mass. So, this is 3.2 grams divided by molar mass, which is propane, is CH3, CH2, CH3, that is 15 and 15, 30 and 14, that is 44. That is the number of moles of propane, and we can now solve for the pressure. So, 3.2 grams over 44 grams per mole times 0.082 liter atmosphere per Kelvin per mole times 293 Kelvin divided by 0.35 liters. So, this goes, this goes, this goes, and this goes, and that should give you your result for the pressure in atmospheres. So, that is straightforward implementation of the ideal gas equation of state. Here is another interesting one. What is the density in grams per liter of ammonia at 0 degrees Celsius and 1 atm pressure if the gas in a 1 liter bulb weighs 0.672 grams at 25 degrees Celsius and 33.4 millimeters mercury pressure. This is a convoluted question. It introduces a lot of things. For example, you are looking at pressure in a completely different unit. This is something 733.4 millimeters of mercury. Very often you will come across ideal gas or gas behavior expressed in, with pressure expressed in many units. This is one unit that you might come across, millimeters of mercury, which is also called the Torricelli, abbreviated TOR. So, 733.4 TOR, and we know that 760 millimeters of mercury equals 760 torr equals 1 atm. You should be able to convert from one unit of pressure to another unit of pressure. Okay? So, so that is the first thing that we will need to do, is to be able to convert pressure from one unit to another. Right. So, we say that PV equals nRT, and in the previous problem we said that N is equal to mass by the molar mass. So, we rewrite this a little bit. We say PV is equal to the mass of the gas sample over the molar mass times RT. And if we rewrite this once again, we say m by V into RT by m, and that should look familiar. This quantity here, mass by volume, is nothing but the density. So, this I write it as rho, you might write it as d, rho RT by m. So, that is what you will need to use. The ideal gas equation slightly written a little bit differently. This is something that might come in handy for you. The relationship between the pressure and the density, again from the ideal gas equation of state. So, you could use this to calculate what you want, and hopefully you will be able to do it, and I will leave this as an exercise for you. In the next session, we will look at deviations from ideality, which we showed for the case of molar volumes, that many gases under identical conditions have molar volumes at 0 Celsius and 1 atm pressure close to but not identical with 22.4 liters, which we will take up in the next session.